So, welcome back. We were discussing about the non-invasive measurement technique, and in that line we have discussed about the Pitot tube. So, next invasive measurement technique is hot wire anemometry. Now, this technique is one of the widely used technique to understand the turbulence in single phase flow, and the technique has also been used to analyze the multi-phase flow. And this is the technique you can say that whatever the understanding of the turbulence experiments we have and initially which we have developed is all because of this technique, and this technique plays a major role to understand the turbulence. And why? Because this technique have a very high response time. Okay, both spatial resolution as well as the temporal resolution of this technique is very high. So, we will try to understand first the basics of this technique, okay, then what is the measurement principle, and then we will try to understand that how the same technique can be used for the multi-phase flow, what will be the limitation and overall advantage and drawback of this technique. So, with this we will start about this technique in this class, and as I said that the name itself is hot wire anemometry. So, you can understand it means that there is some wire is being used which is hot at certain condition, and that hot condition is being used to measure the velocity, and that is why the name is called hot wire anemometry. So, the typically the setup or the kind of probe which is being used to in hot wire anemometry, it looks something like this. Okay, it looks something like this. So, it has actually 4 parts. One is the probe body, which is this, okay, which is actually support to the probe, and the back side of this the electronics is being there, which is used for the measurements. We will discuss about those electronics. Then there is a pronge actually which is being used as a support. Then there is some other support here which you see from this side, and then we use a small wire. This is the wire, because of that the name is hot wire anemometry, and that wire is being used for the measurement. How we will say about that, we will discuss about that. So, this is the active length of the wire, and this is the diameter of the wire, and these are the support which actually hold the wire. So, this technique is being used, and the basic measurement principle of this technique is that it is being connected with this wire is actually one leg of the Wheatstone bridge. Now, we will discuss about the circuit also. So, what happened? We know that in the Wheatstone bridge, say this is a typical Wheatstone bridge. Okay, this is a typical say Wheatstone bridge. If I give a current voltage, then what will happen? A volt difference, then the current will be actually divided based on their resistance ratio, say R3, R4. So, it will be divided based on their resistance ratio, and you can find it out that how much current will be flowing here, okay, in each kind of circuit or each line. Now, if you change the resistance of 1, then what will happen? The overall current distribution or volt distribution will change, and that volt distribution will be proportional to the change in the resistance, and that is the basic principle which we use in the hot wire anemometry. So, what we do? We give certain voltage potential initially. So, because of the voltage potential some current will pass. So, each resistance or each wire will be maintained at a particular temperature. Now, if suppose one of the wire I connect with the fluid, if we are exposed to the fluid. So, this is my fluid leg, this is the wire. Then what will happen? That because the fluid will come, it will change the temperature because of the heat transfer. Now, the change in the temperature will be recorded as a change in the resistance, and that change in the resistance will cause change in the current. And because of that, the change in the current will be proportional. If you will do that, the calculation, we will see the numerical part, it will be proportional to the velocity. So, you can measure the velocity of the fluid, and that is what the principle is, that in this place in hot wire anemometry a hot wire is used. The diameter of the hot wire is in the range of micrometer. This is diameter, is currently is the range of 5 micrometer. Okay. Earlier it was much bigger, but in the current state of art of HWA the wire thickness is very low, and it comes in the range of 5 micrometer. Okay. And the length is around 1 to 5 mm, depending upon the application and different type of the probe. So, one length varies in the range of 1 to 5 mm, diameter varies in the range of say 5 micrometer. This is being exposed, this is wire is being exposed to the flow field or being inserted in the flow field. Now, what will happen? The flow field, actually the velocity can be sensed by the convective heat transfer measurement. So, because of that wire is being there, as I said that there is some temperature will be given because of that particular current or particular volt which has been applied. Wire will be maintained at a certain temperature. Now, if we will expose that wire to the fluid, then what will happen? Because of the fluid, some convective heat transfer will take place, and that convective heat transfer will change the temperature of the wire, and that is why it will change the temperature resistance of the wire and the current. So, what you are actually solving is a very simple equation which you will might have done in your transport phenomena course, in which what we do, a 2D cylinder is being suspended in a fluid. Now, why we are taking 2D cylinder? Because the diameter of the probe is very small. So, if the diameter of the probe is very small, you can always assume it to be a theta symmetric, and you can assume that the temperature is completely kind of symmetric here. So, it is a 2D cylinder something like this, which is suspended in the fluid, and you find the convective heat transfer, and that convective heat transfer coefficient you correlate with the your resistance change. So, that is the basic principle of the hot wire anemometry, by which we record the signal. So, what, as I said already said, but what is the formally the basic principle, working principle of the hot wire anemometry is that hot wire anemometry uses a fine wire, as I said, on the order of several micrometers, in the order of actually 5 micrometer with the current state of the art, which are maintained at a particular temperature. It is heated at a particular temperature which is above than the ambient temperature. Okay. Then what we do, the electrical resistance of the conductor actually is changes with change in the temperature, and hence the resistance of the wire is also changed. And once you put that wire in a flowing fluid, what will happen? Because of the convective heat transfer, the fluid will try to cool the temperature of the wire or cool the wire, and because of that there will be change in the resistance, and resistance will be reduced, and because the resistance will be reduced, the current distribution will change. So, you can do that, and by monitoring that resistance change of heated wire and taking the temperature of the surrounding fluid, if you measure the surrounding fluid temperature, we measure that how much resistance change has been taken place, you can calculate the velocity of the fluid. Okay. So, that is the basic principle which is being used in hot wire anemometry, okay, to understand that. So, what we do actually, again I will come back to the same, that we make a Wheatstone bridge circuit. Say I put some resistance here, I put again some resistance here, this, then again I put some resistance, this, resistance, this. Okay. Now, I connect it to say certain voltage, okay, and I will make it a switch arrangement, and say I am making an amplifier, okay, and this, and then I am giving a voltage difference of voltage. I will reduce it, I will say that I will give a voltage here. So, this is a typical circuit, okay, and this place you can, if you want, you can ground it. Okay. So, what will happen? Say this is my R1, this is my R2, this is my R wire, and this is my R3. Okay. Now, in the hot wire anemometry, what we do? We extend this resistance, and I will make this resistance something like this, that this, and we have extended it and exposed this resistance to the fluid. Okay. And this becomes my RW. Okay, clear? So, what we are going to do, we know that if there will be current will pass with the Wheatstone bridge principle, that it is going to be the ratio R1 upon R2 is going to be equal to RW upon R3. These are going to equal, and that will be at a ratio which will be called as the resistance ratio R, and generally typically we balance a resistance ratio of around 1.5. Okay. So, that is the way this distribution will be there, this R will be here, okay, and the current will be passed through this, if you give a voltage difference, a particular current will be passing. Now, because the particular volt difference we are already giving, each resistance will be maintained at a certain temperature. Okay. So, let us assume that the temperature is Tw here. Now, if I expose this to a fluid which is moving, say in any direction, in this direction, if suppose a fluid is moving, and I expose this wire to the fluid, what will happen if suppose the fluid temperature is Tf, then because of this fluid, the resistance, this wire temperature will cool down, okay, because of the heat transfer. The moment the wire temperature will be cooled down, this ratio will be disturbed, and then what will happen, your voltage will your current will change. Okay. So, what you try to do, you maintain that you measure the change in the current, and that change in the current is actually being converted in terms of the velocity measurement. Okay. By using King's law. I hope some of you might be knowing this in the electrical engineering courses, and even in heat transfer courses you might have heard about that. So, by using the King's law, we convert this change in the resistance in terms of the velocity. Okay. So, that is the basic principle of hot wire anemometry. We use some volt difference, we use some switches, we will discuss this circuit again, and we use some amplifier. Okay, I will discuss this again once again. So, that is the basic principle of the measurement, and based on that we calculate that change in the current or change in the resistance in terms of the velocity. Now, you can do both, you have both the luxury, and we will discuss that what is the type of this. So, as I said that there is different type depending upon whatever you are doing, whether you are maintaining the current change, or you are seeing that resistance change. You can divide the hot wire anemometry in different parts or different types. Now, the types has been divided based on number of wires and also based on the mode of operation. So, we will discuss the mode of operation. Before that, I will discuss that number of wires that has been kind of divided. The first one is called single wire, as I have discussed, and the photograph I have already shown you. This is a single wire anemometer. So, what it does that the single wire anemometer is being placed in the flow. Okay. So, suppose this is the flow, the fluid will be passed it in this way. Okay. So, that say this is the fluid. What will happen? Now, the fluid will pass, cylinder has been exposed through the fluid, okay, and it will be like a passed flow immersed body. Now, this cylinder is being exposed because of the fluid temperature or fluid velocity and convective heat transfer. The temperature of this cylinder or this wire will be reduced, and you can convert that change in the resistance in terms of the velocity. Okay, so, you can measure the velocity. But what happened with the single wire, that it can measure only the one directional velocity, or if there is only longitudinal velocity it can measure. But if you have a two dimensional velocity, it means longitudinal as well as transverse velocity is there, it cannot measure that. So, in that case we use a X wire type of hot wire anemometer. So, what it does, the same thing, the fluid is being flowing it in this way with a particular velocity. What will happen, both the wire will get cooled down. Now, both the wire is connected to individual Wheatstone bridge, the current will the temperature will be modified. If their temperature is modified, what is going to happen? Their resistance is going to be modified, and the current will also be changed. So, again whatever you are measuring, you want to measure the change in the resistance or change in the current, you can calculate the velocity, and you can calculate both the velocity, both directional velocity in this. How you can calculate that, we will discuss again in the mathematical part of it, once we will discuss the mathematical part. Now, if suppose you have all the three dimensional velocity, okay, then we use the triplet wire, okay, or triple split. So, this is the name is being used, some people say triple wire, some people say triple split wire. There is a three wires are there, again each wire is an individual Wheatstone bridge. It will measure that what is the change in the temperature because of the fluid flow, and the change in the temperature will be recorded in terms of the change in the resistance or in terms of the change in the current. So, you can again measure the velocity. So, what happened that, as I said, that with the single wire you can allow to measure the only longitudinal velocity and velocity fluctuation for sure. Okay, that is the major advantage of this, you can measure the velocity as well as the velocity fluctuation. This allow you, X wire allow you to measure the transverse velocity and velocity fluctuation, that will be always been there. The three wire will give you not this the sign and value of the two component of the velocity, and they can measure simultaneously both the components of the velocity, and definitely they are going to provide the fluctuation too. Okay. So, depending upon what kind of flow you have one dimensional flow, you have longitudinal flow, transverse flow, or two component of the velocity, whatever you want to measure, you can use the number of wires and you can measure that. Okay. So, that is one way to divide the types of hot wire anemometer. Second way, which is critical actually, on the mode of operation. So, as I discussed in the circuit, that what will happen, that you are going to see the change in the resistance. Now, based on that, and then that change in the resistance can be recorded in terms of the change in the current. Now, based on the mode of operation, how you want to operate, the hot wire anemometry is actually being divided mainly in two parts. That one is called constant current hot wire anemometer, and second one is called constant temperature hot wire anemometer. Now, as the name suggests, that in the constant current you are going to keep the current same, and in the constant temperature you are going to keep the temperature same. Now, temperature same means resistance same. So, you can also say that is a constant temperature. Some people also say constant resistance. So, both are same. Okay. So, you can make the constant resistance or you can make the constant temperature. So, that is the way it has been divided. Each technique have their own advantage, or each mode have their own advantage and disadvantage. However, mostly constant temperature hot wire anemometer is being used. Why? We will discuss. So, now what is the constant current hot wire anemometer? As I said that constant current hot wire anemometer means you will maintain the current constant and you will change the resistance. Okay. So, that is the way what is called constant current. Constant temperature means you are going to keep the resistance same by using some servo amplifier, okay, or feedback controller, and you will keep on changing the current. Okay. So, that the overall resistance you are going to keep on same. Okay. So, that is the basic way it has been defined, the constant current and constant temperature. We will try to understand that. So, what is the constant temperature? In constant temperature mode, what we do, the current through the wire is adjusted to maintain the constant temperature. So, how the temperature will be given? If I maintain the current constant, okay, then what will happen that if you want to maintain the temperature constant, what you need to do, you have to vary the current. So, suppose this is the Wheatstone bridge, again I will make the same. So, this is my say Wheatstone bridge circuit, okay, and say this, and I am going with this I put a switch. Okay, then I am coming here, I went for a servo type amplifier, and then I have given a voltage difference. Now, what will happen? Initially say R1, R2, RW and R3. Okay. They are maintained, and this is maintained at temperature TW. Now, if you expose it to the fluid, say if I expose it to a fluid, then what will happen? That the temperature of this wire resistance will change, and because of that the RW will also change. Now, the moment RW will change, the ratio of the resistance will change, and you need to supply the extra current, okay, to maintain the same temperature. How? Because if you want to maintain the same temperature, the same current should be supplied in this leg. If the current will be the same, the overall temperature will also be the same. So, what you need to do, now it has been cooler down, resistance has reduced. So, you have to increase the current so that your power to this wire remains same. Now, to improve that current, what you will do, you will use the servo type amplifier, feedback amplifier, and that amplifier will actually pass the current. If it will suppose cool down where it is then there, so what will happen, this switch will be not disconnected and the current will be stopped, and you will see that the temperature of the wire has changed. Okay. So, that is the main circuit is being used, and you use the amplifier. If you want to use the constant current amplifier, then what you have to do, you have to keep the current similar. Now, to keep the current similar, what you need to do, you have to maintain this ratio same somehow. So, R1 upon R2 should remain same as RW upon R3. So, what you will do, you will put a extra resistance here somewhere, and that resistance you will be manipulating in such a way that your ratio remains same, this ratio remains same. So, the circuit is almost same, only you maintain, instead of varying the kind of current by using the servo type amplifier, you are now varying the resistance, so that the resistance ratios remain same. So, that is the basic which we use in constant temperature and constant current. Okay. So, that is what we have said, that what will happen, that because of the flow the temperature will change, and the temperature need to be maintained, and that will be maintained by supplying the extra current, because the power will remain then same, it is equal to I square, P is equal to I square R. So, if the change in the temperature is causing change in the resistance, if I increase that current, what will happen, your temperature will again be increased, okay, because I square R value will remain same. So, that is the way we do it. Now, we use to do that current manipulation, we use a feedback circuit. So, this is the feedback circuit, we kind of see that how the current is being reduced, based on that we amplify the current, okay, and that is the way it is being done. So, what is there, that it should be clear that the current required maintaining the wire at a constant temperature is going to be proportional to the convective heat loss. Okay. So, more the heat loss, more the current you will require. So, that is going to be the proportional, and that proportionality will actually can be related with the velocity, and because heat loss, the convective heat loss is a function of velocity, we all know that, and so the velocity can be measured or can be correlated with the increase in the current requirement. Okay. So, that is the principle which we use for the constant temperature hot wire anemometer. Now, in constant current hot wire anemometer, as I said that what we do, we maintain the constant current mode. Okay. So, constant current means your constant heat use there. So, what you are going to do? You are going to fit a electrical current flow through the wire, and that is what will happen, that we have to kind of pass approximately same current through the wire. If you will pass the approximately same current through the wire which is being exposed, as I said that I square R value will remain same, and then you will have maintaining the constant current. Now, though I square R value will not be the same, but you will maintaining the constant current. Okay. So, that is what is the objective, that you have to flow the constant current through the wire. Now, that is been possible to attain that the equilibrium temperature will change. Okay. And that equilibrium temperature between the internal heat generation due to the electrical resistance, okay, and the convective of wire, convective heat conduction of the wire, okay, or convective heat transfer of the wire to the moving fluid will be actually get balanced. Okay. So, they will be equilibrium. So, that way what you can do, that the wire temperature change, okay, must be adjusted with the convective loss, okay, until the equilibrium of the temperature is achieved. So, what will happen, because we are keeping the temperature current same, that the temperature is going to be changed. Now, how much temperature of the wire will change, that will depend on how much heat loss has been taken place from wire to the fluid. Okay. So, that will be the temperature change will be recorded, and that temperature change will be actually the function of velocity, because again the convective heat transfer. So, the temperature change on the wire will be actually the function of the velocity of the fluid, because how much temperature change you are going to see, that how much convective losses are taking place from the wire. Okay. So, in that way you can again correlate the temperature change recorded to the velocity of the fluid, and the velocity of the fluid can be measured. Okay. So, that is the constant current hot wire anemometer is being used, and the circuit what we do, we put some additional resistance and we keep on changing that resistance in such a way that your current flow should remain same. Okay. So, that is the way, that is the principle of the constant current hot wire anemometer. Now, obvious question will be which one I should use, whether I should use the constant current or should I use the constant temperature. So, now you can compare. So, what is the basic principle or basic difference in this? In the constant temperature hot wire anemometer, okay, is used in the same way it is being calibrated. Now, as I already said earlier in the introduction class, that most of the measurement technique is not the direct measurement, you are not directly measuring the velocity per se, you are measuring some other quantity, and that quantity is being calibrated in terms of the velocity, or is kind of being recalculated in terms of the velocity. So, in such measurement which is indirect measurement, definitely you need to do the calibration, and calibration is very, very critical, and the accuracy of your measurement actually depend on the accuracy of the calibration, and I will keep on repeating this thing, because most of the technique we will discuss will be actually doing the indirect measurement. So, the calibration becomes a very, very integral part of all the measurement techniques. So, in this also you do the calibration, and while doing the calibration, the standard procedure is to maintain the temperature of the wire same. Okay. So, it means the major benefit of the hot wire anemometer, which is operated on the constant temperature mode, that the way you do the calibration and the way you do the measurement is remains same. Okay. So, that is the major advantage of this, because it enhances the accuracy. Okay. Then in constant current, what happens, as I said that in the constant current also the calibration is performed by maintaining the constant temperature, and then that is being converted in terms of the constant current. So, what you have to do, you have to again do a conversion, and then that conversion will be again being converted in terms of the velocity. So, one more extra layer of the conversion is coming, and that is why we would like to prefer the constant temperature, because you are doing the calibration and measurement exactly in the same way. While in constant current you do the calibration by using the constant temperature approach, you do the measurement by using constant temperature mode. So, that makes a difference and that may kind of hamper little bit of your sensitivity of the probe. So, that is the major thing. Then the major disadvantage of the constant current hot wire anemometer is that wire burnout. Now, what does the wire burnout means? Because we are actually allowing to change the temperature. Now, if you allow to change the temperature in the constant current mode, what will happen if the temperature increases beyond a certain point, the wire will burn out, or if the temperature reduces below a certain point, it means the resistance will be very low. So, the power, the current flow can be increased momentarily before you get into control into it. It can burn the element itself, it can burn your wire. So, that risk is very high in case of the constant current hot wire anemometer. While in constant temperature hot wire anemometer, the wire temperature always remain constant. So, wire burnout is very low, again because of some fluctuation, some instability or some kind of error performance or kind of your not good performance of your controller, it may kind of burn, the wire can burn. But most of the time the probability of burning wire in case of the constant temperature hot wire anemometer is very low, okay? And that gives a major boost again, because the cost of this hot wire anemometer, if you buy from any kind of commercial vendor like Dentec and all, the cost is very costly. It's not very cheap technique like a Pitot tube. It will be costly technique. So, definitely you don't want a burnout of the wire, and because of that again constant temperature hot wire anemometer is being preferred, okay? And again, as I said, that life of the sensor in the constant temperature hot wire anemometer is higher, not only because of the burnout possibility is low, but also because the wire is always maintained at a particular constant temperature. So, it need not to go from the thermal shock or thermal cycle. In the constant current, what will happen? The temperature of wire will keep on changing. So, sometimes it will reduce, sometimes it will increase. So, you will always having a thermal cycle of the from the wire or during in the wire, that sometimes it is being heated, sometimes the temperature is going down. So, that will again what it will do? It will reduce the life of your wire, and that is the reason that most of the places constant temperature hot wire anemometer are used. But again, it does not mean that you cannot use constant current, you can do that constant current also, but the constant temperature is being preferred because the life of the constant temperature wires are much higher compared to the constant current probes or constant current wires, okay? And then the calibration is always an edge. So, this is the major advantage that why the constant temperature hot wire anemometers are used. Now, these hot wire anemometers, though we can buy from a commercial vendor, but ideally speaking you can also prepare the hot wire anemometer at your place, and it is very simple to make. You just need a wire made of tungsten or platinum. So, both of this most of this wires used in the hot wire anemometer is either made of tungsten or made of platinum. Sometimes they are mixed materials also. So, you need just a tungsten wire or platinum wire. You have to maintain a large L by D ratio. As I said that the length is in the order of 1 to 5 mm and dia is in the order of 5 micrometer. So, if you see that L by D ratio is going in the range of 1000, if I take 5 mm and 5 micron. So, in the range of 1000, we keep a very large your L by D ratio. Now, why we keep a very large L by D ratio is important, because if you remember the picture, and I will take you back little bit, that if you remember this picture whichever I have shown, that how it will look like, there will be a pronge or support which will be held this support. So, I will tell it as a pronge, okay. This is actually the support which is holding the wire, and then this is the wire which is being used for all the measurement. So, what will happen? If your wire diameter will be high, then conduction losses from the wire to this support will be higher. Okay. Are you getting my point? So, let me explain again. Suppose this is the support what I am talking about, and this is a pronge. This is a pronge. In between that there is a wire. Now, if suppose the wire thickness is very small, then what will happen? Because this wire is being heated, there will be conduction losses from this wire to this supports also. Okay. Now, if the wire thickness is very small, the contact area will be very small, and in that case you can say that the losses because of this conduction is negligible compared to the loss because of the fluid motion, which is the fluid motion is being caused, the convective heat transfer loss. But if your wire thickness is very big, suppose now you have increased the wire thickness something like this is now your current wire thickness, then what will happen? Your contact area is very big, so the conductive losses will also be higher, and you cannot neglect that, you will not be in a position to neglect that. So, your calculation will be much difficult, we will see the mathematics part, we will see that how you do the measurement, but your calibration will be very typical, and we will show you that why it will be typical. You have to take additional term into the account, that will be the conductive loss to the support or to the pronge. Okay. So, that is the way it has been there. So, that is why the L by D ratio should be higher. Okay. Why the L need to be higher? Because we know that the L resistivity of the wire depends on the length and the area both. So, if you increase the area, resistivity will increase, if you increase the length, resistivity will also increase. You need certain resistance, so that there will be a particular temperature will be maintained, neither it will be burned out even at a small current pass, I square R values. If this is R is very low, the resistance will be very low, it will burn out immediately. So, you need certain length, so that you can maintain certain resistivity. So, that is why you are not doing that with increasing diameter, but you are doing that by increasing the length of this wire. So, that is the reason that why the L by D ratio should be very high in such a kind of a probe to measure the conductive losses to the support. Okay. Then again, the smaller diameter will increase your response time. Why? Because if the diameter is small, if you suspend it in the fluid, the temperature of this wire will suddenly get uniform, very fast it will get uniform, because there is no radial variation and the whole length is being dipped in the fluid. So, the lengthwise the temperature will be the same, and there is no diameter, there is no radial temperature gradient. So, it will maintain, it will show the temperature difference very fast. If you suppose have a very big wire in this way, then what will happen? Even if you suspend in the fluid, it will take some time before the temperature becomes uniform and constant everywhere. Okay, it will take some time. So, what will happen till it will not take that time? What you will see, you will keep on seeing the change in the temperature and change in the resistance, whatever the mode you operate, whether the constant temperature or the constant current. In both the places you will see the problem. So, what will happen? It will reduce its temporal response. Why? Because you have to wait till it is not coming to a constant temperature. So, smaller diameter actually increases the temperature response, and the temperature response of this technique is very high. We will discuss that, is very high, because you are using a very thin wire. Further thing, it maximizes your spatial resolution. Now, hot wire anemometry like a Pitot tube also gives a point measurement. So, what does it mean? Because there is only one wire and which is being exposed. So, this is my hot wire anemometer. Okay. Sorry. So, this is being exposed to the fluid. Now, this is being exposed, this is the pronge. Now, this is being exposed to the fluid. So, what will happen? It will measure the velocity at this location only. It cannot give you the velocity distribution or radial velocity distribution. It cannot give you the velocity everywhere in all the flow fields. Suppose if you put it inside the column, it can give you the velocity at a particular location only. It cannot give you the velocity at all the locations. So, what will the possible way? If you want to measure the velocity at all the location, you have to keep the wire at all the possible locations. So, initially you put it here, then you put at this position, then you put at this position, this position, this position. Now, what is spatial resolution? How close you can measure the velocity? Smaller the thickness of the wire, smaller will be that distance, okay, and maximum will be the spatial resolution. Say if I use a wire of thickness 1 centimeter, the next point will be minimum after the 1 centimeter. So, suppose if I take the wire of 1 centimeter of diameter, okay, the next point will be, even if I keep it just next to it, it will be like this. If it will be like this will be 1 centimeter. So, center to center distance also remain 1 centimeter. So, what will happen? Your spatial resolution will be limited to 1 centimeter. Okay, clear? So, the smaller wire thickness actually maximizes your spatial resolution. It minimizes your noise, okay, it reduces your noise and improves your signal to noise ratio. Okay. It also reduces, and this is most critical, the intrusive nature of the probe, because you are now reducing the diameter. So, the effect will be much lower compared to the bigger wire effect. So, suppose if you are putting a 1 to 5 micrometer your diameter wire, there will be some change in the probe velocity field. I am not saying there will be no change, there will be some change, but that change will be much lower compared to if you intrude a probe which is of 1 centimeter in diameter. Okay. So, that is the major reason and how the wire dimension should be taken place and why it has been taken place in this place, and what should be the material. Definitely material should be very conductive and it should have certain resistance to vary the temperature. So, thermal resistance as well as the electrical resistance of the material should be very good and it should be conductive it should be very conductive. So, that is why the tungsten and platinum are generally used for the wire material. Now, coming back to the measurement principle, whatever we have discussed, now we can see that how exactly the things happen. So, what I have said till now, that suppose there is a hot wire anemometer, means there is a wire and that wire is being suspended in a fluid, and we maintain that this wire is maintained at a temperature Tw, resistance is Rw, say area is As, that is the wire. Okay. So, Tw we will write it anyway. So, now if you suspend in the fluid, what will happen? There will be heat transfer taking place, because wire is maintained at a certain temperature, fluid is maintained at a certain temperature. So, because of that temperature gradient, there will be some heat loss. Now, what will be the heat loss or total heat loss? Say if I write it in terms of the Q. So, the total heat loss, I will say the Qt will be what? It will be because of Q natural convection, I will write it as natural convection, that will also take place, plus Q forced convection plus Q of R radiation to the surroundings plus Q C conduction, and we will say that conduction to support or pronge. So, that is the way the heat transfer losses will take place. So, what will happen? The fluid will be there, it will be taking the heat through the natural convection, it can take the heat through the forced convection, there can be radiation losses, okay, and there will be some conduction losses. Now, as I said that if the diameter of this wire is very small, the conduction losses to the pronge can be neglected. Anyway, first let us see that how to mathematically write it. So, for natural convection, what we know? We know that there are several equations available, we can use that. For the forced convection, the equation is generally we use Newton's law of cooling. So, H is heat transfer coefficient into As, okay, into Tw minus Tf. That will be the natural convection, that is heat transfer coefficient As is surface area of wire, Tw is wire temperature, and Tf is fluid temperature. Okay. Now, the radiation, we know that Stephen-Boltzmann equation we can use. So, it will be A S star sigma star epsilon star Tw4 minus Ta or Tf4. Okay. So, we can do that. Emissivity, okay, is the Stephen-Boltzmann constant sigma, surface area, Tw and Ts. And then the conduction losses can be written, Qc can be written as minus K into As, okay, into dt upon dx. That will be the conduction losses. Okay, clear? So, we can have this equation, and ideally if you want, the total heat loss will be because of this. Now, we know that if the wire temperature is very small, okay, or is relatively smaller, not very small, then I can neglect with kind of QR value, and it will not generate much error in my measurements, okay, and it will simplify my calculations. So, I can neglect the QR value if the temperature difference is very low or it is not very high. Similarly, if your wire is very thin, okay, you can say that the convective losses or conductive losses to the pronge or to the support can also be neglected. If the velocity is there, if the fluid is moving with the velocity and sufficient velocity, the natural convection part can also be neglected. So, what is going to happen? The heat loss which is going to take place from this wire will be purely because of the convective heat transfer. Okay. So, this QT will be equal to actually QFC, and that will be equal to H into AS into TW minus TF. That will be your total heat loss, okay, which will be taking place from the wire. Now, we know that how the wire temperature will change or resistance will change with this heat loss. So, for that we know that equation, we know the correlation between the wire resistance and the temperature, and that is being given, say RW or of reference, say a reference temperature or reference resistance which was there earlier, 1 plus or constant alpha, it will be T of W, T of fluid, okay, minus T of reference. Okay. So, that is the way it has been maintained, that the way it will be there. Okay. So, in this way it will be maintained. So, RW will be what? It is the wire resistance RF is reference resistance, Ts is the surface temperature of the wire, better we write the same term as a TW instead of Cs. Let us not kind of simplify this equation. So, we can say TW, and T reference is the reference temperature. Temperature at reference resistance. Okay. So, that is the way we know that how the RW is changing. Okay. Now, we can use that equation QT is HATW minus T of fluid. This is A of surface AS. Now, this is the convective heat transfer. Now, we know that from the King's law that heat transfer coefficient is also a function of velocity, and how it has been related to the velocity. H is being related to A plus B into V, where V is the velocity raised to the power C, and generally this value of C is equal to 0.5. So, you can say that it will be A plus B into V raised to the power 0.5 H. What we can do? We can replace the H value here in the QT by this equation. So, your equation will be modified, and your equation will be, instead of H you will get A plus B V raised to the power 0.5 into AS into TW minus TF, okay, and that will be equal to QT. Clear? Now, this QT, the heat transfer will be take place. How much heat transfer will be take place? It will be equivalent to how much power supplied to the wire. So, that is the heat transfer which will be taking place, or the kind of overall heat transfer will be there. So, whatever the voltage drop or the power will be given to the wire, that will be equal to the convective heat transfer loss once the equilibrium will be achieved at this condition. Okay. So, it means QT, the power to the resistance supplied to the wire, will be exactly what? We can write it in terms of the I square RW, which I is nothing but the current. Okay. You got my point, that the electrical power input will be equal, okay, to the convective losses. So, electrical power input to the wire will be equal to the convective losses based on this convective loss temperature. So, you can write it I square RW will be equal to H A TW minus TF. H I have converted in terms of the King's law. So, you will get it in this value. Okay. So, you can write it here I square RW will be equal to A plus V into V raised to the power 0.5 into AS into TW minus T of F fluid. That is the way we can write. RW again you can convert in terms of the T and TF. So, in terms of the reference. So, I square you can say will be equal to A plus B V raised to the power 0.5, okay, into AS, that will be into AS Tw minus Tf, and this Rw can be written as R reference 1 plus alpha, it will be Ts or Tw minus T reference. So, that is the I square value. Now, it means what it says? It says that your current change is directly proportional to change of the fluid temperature, and that fluid temperature is measured with the velocity. So, if you are measuring the current change, if you are measuring the fluid temperature, what you can find? You can easily find that what is your velocity, because you will get that R value also, okay, that how your resistance value will change with this formula, whatever I have done. So, if you know your reference temperature, you know that how much temperature you have changed, your reference temperature also you know, you can calculate the velocity. So, what you need? You need fluid temperature, you need I square. If you know that, you can calculate this value. If you do not know that, what you can do? You can convert it in terms of the constant temperature. If you maintain the temperature constant, okay, you can find that how much current value need to be accounted. So, either you can keep this I square constant, or you can keep this temperature difference constant. Okay. So, the temperature constant will be there, this will be constant temperature, and you can measure the correlation, you can measure the velocity, and the equation will be simplified, and you will get that what will be the velocity for say constant temperature if we do the anemometer. Finally, this you can write I in terms of the V square. So, this will be I square will be V square upon R square, it will come, this will be cancelled out, and it will be simply as a King's law, A into B raised to the power 0.5. Here the V is volt, so I will not confuse it, I will write it as a E square, where E is volt. Okay. So, what is the volt supplied? So, I is equal to V upon R. Okay. So, you do that, or not B upon R, say, because sorry I am just doing this. So, E upon R, where E is the voltage. So, we can measure the voltage difference, and that voltage difference can be measured in terms of the velocity, and in most of the constant temperature anemometer, okay, this is constant temperature anemometer, constant temperature anemometer, we can reduce it into this form, E square is equal to A plus B into V raised to the power 0.5, 0.5. We can find it out the A and B value, and we can see that how this E, V and V is being correlated, and what you need to do that you have to do the calibration. Okay. If you do the calibration, you will find that how the E and V is correlated. In the constant temperature anemometer, you do the experiments, you maintain the temperature constant by changing the voltage. It means you have to change the kind of voltage or current in any way, whatever you say. You measure the volt difference at the outlet, and you will find that how the velocity will be, what will be the velocity. So, what we do? We do the calibration, and in the calibration what we do? In the calibration part, we suspend the probe in a domain, say this is the fluid field, okay, or and I suspend the wire here, I suspend the wire, so this is the probe, I suspended it here, somewhere here in this way, the pronge, okay, I suspend the wire and I measure that velocity. Now, how I measure the velocity? What I do? I put a Pitot tube, and that is the way the calibration is being done in hot wire anemometer. So, I put a Pitot tube, and that Pitot tube is being connected to say a manometer. You measure the H, we know that velocity in this Pitot tube is going to be under root 2 into G H, or you can say rho p my p into rho p minus rho, and p I have just converted in terms of the manometer reading. So, it will come into under root 2 rho G H. Okay. So, that is the way you can calculate the velocity, and you can record that volt, that what is the volt difference. Say you put a circuit where voltmeter is there, you can see that what is the volt is recorded. So, what you can do? You can put a plot between E square and V raised to the power 0.5. If you put that E square, whatever the formula we have get is A plus B into V raised to the power 0.5. If I plot a graph between E square and V.5, what I will get? I will get a straight line which will have an intercept. The value of intercept will be A and the slope of line will be B. So, you will get this calibration parameter, you will get the value of A, you will get the value of B, and then what you can do? You can calculate that what will be your velocity. Okay. Now, in the real experiments here, what you were knowing? You were knowing that at this velocity, what will be the volt difference, In the real experiments, you will be measuring the volt difference and you will be calculating the velocity. So, you will get that what is the velocity of the fluid, and not only the velocity. Now, what will happen with the change in the current? If there is a turbulent flow, and that is the reason why it is being used so fast, because the temporal response of the electrical signals are very high. It can go up to 1 megahertz. It means you can acquire at 10 to the power minus 6 seconds data acquisition time, delta t. So, what will happen if you do that? You will see that you can find this flow, you can acquire the data at a very high speed, and if the flow is turbulent, if the fluctuations level is very high, you can acquire at a very high frequency, and you can not only get the velocity, but you can also get the fluctuations, that how the fluctuation is taking place. So, with each fluctuation, the temperature kind of will try to be modified. You will keep the temperature same, current will be modified, a volt will be modified, and you will see the volt fluctuation reading, and this volt fluctuation reading get it in this way with the time, and this volt fluctuation or E versus T you can get. This can be calibrated with the velocity, that how the velocity will be there. You can calculate the mean with the time average mean value. You can find it out how what will be the fluctuating component of the velocity in this case. Okay. So, you can do all this with the hot wire anemometer, and that is why this technique is very famous and being widely used. Okay. Now, I would like to also do the comparison between hot wire anemometry and Pitot tube, because we are calibrating the hot wire anemometer with the Pitot tube. You should not confuse that it is only as good as Pitot tube. So, what is the comparison? So, the major comparison, major advantage that the Pitot tube, because the response time is very low, the manometer will take time before it will get stabilized. It can measure only the time average mean velocity, while hot wire anemometer, the frequency response is very high. So, what you can measure? You can measure the fluctuation velocity, you can measure the real time fluctuation velocity, you can measure the mean velocity for sure. Okay. The advantage of the Pitot tube and why it is being used also is that there is no calibration required. You are using Pitot tube to calibrate hot wire anemometer. So, no calibration is required. Definitely the cost is much lower than whatever we are using in the hot wire anemometer. So, the cost factor is also coming to the picture. It is very cheap compared to the hot wire anemometer. Okay. The major thing is that the hot wire anemometer calibration is very typical, critical, and it is not a very easy job. It is a time consuming job. You have to do the calibration for sufficient long time. Then only you will get that, and as I said, accuracy of your hot wire anemometer measurement will depend on the accuracy of your calibration curve. So, you need to prepare the calibration curve properly, and the calibration in HWA is performed using the Pitot tube to obtain the correlation coefficients, okay, to measure the speed at the and outlet voltage. So, you can find that correlation only by using the Pitot tube. So, that is the way. So, hot wire anemometer, the major advantage is your frequency response time is very high. It means the temporal resolution is very high. Ideally speaking, you can achieve very high spatial resolution if you use an array of hot wire anemometer probes, okay, or you keep the probes at several locations. You can ideally speaking can use achieve a very high spatial resolution too, and it can give you not only the mean velocity, it can also give you the fluctuating velocity and real time fluctuation velocities. So, that is the major advantage of the hot wire anemometer over the conventional Pitot tube. Then the same approach, because it was being used very widely, and in 1942 to 48 this development has been done for the single phase flow, and then many people have used this for the single phase flow. And again I am telling that most of our understanding on the turbulence is generated with the data obtained for the hot wire anemometer. Now, the same concept in late 1970, okay, we use for people have tried to use for the multi-phase flow. So, in the multi-phase flow, all they were whatever I have said is remain same. What you can do, you can use single wire, you can use X wire, you can use triple split wire, depending upon what kind of a velocity coefficient you have. Definitely the single wire have a very limited use, because most of the multi-phase flow is having at least 2-dimensional velocity, if not 3. Okay. Even if you assume the theta directional symmetry, you will have the 3-dimensional velocity or at least 2-dimensional velocity. So, you need to use either triplet or X wire. Most of the time this triple split wire is being used in the multi-phase flow. Then there is additional complexity. Whatever the equation I have solved, it is solved for only one phase, because each phase we have not accounted that heat capacity of that phase. Now, because water and gas have a different heat capacity values, what is going to happen that your heat transfer will be different in case of the water, or a temperature difference will be different in case of the water is touching the wire and in case of air is touching the wire. If suppose you are operating a constant temperature. So, if you are using a constant temperature anemometer, then the current requirement to maintain the constant temperature once the air comes into the contact and once the water comes into the contact will be different even if they are moving with the same velocity. So, what you need to do? You have to do the double level calibration. One, the calibration will be only with the water to see that what will be the volt label. Once the calibration will be only with the air and you have to see the what's the volt label. And you will able to measure the velocity of both the phases only and only if the volt label readings are different for both the phases, like it has been done by Davis in 1972. They have done the experiment with air and water and they have found that with the air and water with the hot wire anemometer, the volt labeled readings are different. Air gives a certain volt of this range and whenever it water comes, the water volt reading is this. So, now you have the reading, volt reading. For each volt reading, for each phase you have to do the calibration, you will find that velocity. Even if you want, you can also find the volume fraction. In the same paper they have tried to show that each curve you will show that how much is the contact time, it will show that how much fraction of the time that phase was staying at that time. You are measuring that fraction, the area under the curve with the time, that will also give you that what will be the fraction of that phase. Okay. But whatever we are interested in mostly in the hot wire anemometer is the velocity measurement that you can easily do here. Okay. The only thing is it will be typical, it will not be that easy. Why? Because you will have the multiple components here. Okay. Now, the second thing which is important is that how to measure the velocity or two dimensional velocity particularly. So, what you can do, if suppose I use a X wire, I will just show one example, triplet will be the same, you can try to do that. So, suppose if I am using a X wire, okay, and there is a velocity in this direction. Okay. Let us do it with the one wire which is being inclined. Okay. Now, this is say velocity, this is the, you are going to get it in this way. Okay. Now, this say is u and this is being converted in curve of u this, okay, and the other thing is converted in terms of the u this. Okay. So, this is the way it has been converted, this is u effective, you are doing it in this way that this is say u effective, this is your u of x direction, this is your u of y direction, okay, and this is your angle which it is making with the wire. Okay. This is your theta, say this is theta, this will be 90 plus theta, okay, 90 degree. So, what will happen? U effective you can convert in terms of this. So, u effective will be what? U effective will be equal to u x, okay, this will be cos 45 plus u y into cos 90 plus 45, 90 plus theta, sorry, this will be theta, this will be theta, cos theta plus 90 plus theta. Okay. Now, this will be what? U x minus u y cos theta. So, if I know the angle between these two, if what is the angle of this slope, then I can find it out that what will be the u effective. Okay. Most of the time this angle is kept 45 degree. Okay. So, this angle is most of the time is kept 45 degree, okay, not centigrade, 45 degree. So, what will happen? The cos theta will be cos 45. So, you can say u x minus u y cos 45 and cos 45 value is 1 upon under root 2. So, you can say u x minus u y 1 upon under root 2. Okay. For the probe which is coming at it in this direction, it means the probe is placed it in this direction and the fluid is coming from. So, probe is in this direction and fluid is coming from this side. Okay. Now, if the probe is in the opposite direction, okay, if the probe is in the opposite direction, say in this way, and the fluid is again coming at it in this way, in this direction, what will happen? Again you can do that, okay, that say this is the fluid direction is coming, this is 45 and this is the another direction. So, what will happen? Now, it will be theta. So, it will be say this is your u effective, this is your u x, this is your u y. So, what will happen? This will be 45, it will be cos u effective, u x will be equal to what? U effective will be u x cos 45, u y cos 45 and you will get that values and that value will be equal to that what is your value. So, this will be u x cos 45 plus u y cos 45 and this will be u effective will be equal to your u x plus u y 1 upon under root 2. Okay. I hope you got that point, that in one case what we have done, we have said that because this is the way this wire is there. So, if the flow is coming at it in this way, this will be the angle. So, that angle will be it will be 90 degree for the ux, and then the u effective will be more than that theta. In this case, once the wire will be on this side and the fluid is coming at it in this way, it will be within the theta. So, that value will be within the theta. So, it will be 45 degree here. Okay, if the wire angle is 45, this will be also at u effective will be at 45 degree. So, it will be ux cos 45, uy sin cos 45, and you will get that ux plus uy 1 upon under root 2. So, we will get the u effective values. We know that for each wire is, say I will say E1 square will be A1 plus B1 into V raised to the power 0.5, okay, and V is nothing but is V effective or U effective. Now, U effective can be written for depending upon E2 will be A2 plus B2 into U effective 0.5. This also let consume U effective, okay, 0.5. Now, this U effective can be written based on that which wire we are talking about, the upward wire or downward side wire, it means plus 45 or minus 45 wires. We can have the values, we can have replace the U effective from this place, say this will go here, let us say this is going here, we will replace that, we will do the calibration, one for the this wire, another for this wire, you will get the constant. So, you will have now 2 calibration curve, that is why it will becomes typical. In chiplet, you have to do it 3 times. Okay. So, you can do that and you can have different wires to measure all the direction velocity, the basic principle again remains same. Okay. So, now concluding this part of hot wire anemometer, what I will say that advantage of the hot wire anemometer, it has the major advantage that is a very good frequency response. It means the temporal response is very high, that is the major advantage. It can measure the velocity and the velocity fluctuation over a wide range of distribution, not in a small range. So, you are not very worried about that what is the velocity, you are worried about the lower velocity, we will see why. You can use it for temperature measurement also actually, because you need the reference temperature. You can calculate the turbulent quantities because you are using the fluctuation velocity, you can calculate the turbulent quantities like vortices, dissipation rate, etc. All the turbulence quantity you can calculate. Okay. It can be measurement containing the continuous turbulence flow, and it can be used even for the bubbles, like in the Pitot tube the problem as we discussed that if you use for the bubble flow, bubble can burst and then the local pressure difference will be very high. So, in case of multi-phase flow, the Pitot tube applications are lower compared to multi-phase flow, because if you have a distributed bubble you can simply use this, okay, the way I have shown the example. But it does not mean that it has all the advantage, it has several drawbacks, and that is why the use is limited and advanced techniques, more advanced techniques are needed and being invented. The major disadvantage is it is intrusive in nature. So, even if we are minimizing the size of the wire, we are not able to minimize the size of the probe. So, size of the probe or support or pronge is actually little bit bigger, and that actually create the invasive nature a lot, you cannot minimize that actually, and that is why the flow can change at the point of measurement itself. Okay. Then the second problem is you are using a wire, and if you are using it in a fluid which is contaminated or having deposition this tendency, or it has been already contaminated with some solid or something, some chemicals, what will happen? The deposition will take place on the wire the moment you will expose it to a surface. The moment the deposition will take place, what will happen? Your resistance will change, your overall calibration will also get modified. So, that is the major problem, that in case of impure environment where deposition tendency is there, you cannot use it. The probe can break in the solid environment. If you put it in the solid, it will immediately break. Can also be break due to the burnout, which will be because of very low temperature, very low velocity or very high temperature. Why the low velocity? Because the low velocity will not able to remove the heat properly. So, that the burnout is possible. You can use array of multiple detector, multiple anemometer is used, hot wire anemometer, to find the radial distribution of the velocity. So, overall the cost, if you want to find the radial distribution, will be very high. The calibration is only valid with a certain velocity range. If you go outside of that velocity range, you will not able to use that, you have to actually calibrate it again. Okay. In the flow of speed is too low, assuming the force convection is not valid, you cannot use the equations which we have developed. If there is a natural convection is also taking place, if the velocity is too low, you have to include that, and then the process will not be very simple. Okay. This assumption of force convection will not be true. Okay. And the major disadvantage is this, that if you have a reverse flow somewhere in between, then your hot wire anemometer will still measure the velocity, it is not going to tell you anything about the direction. So, you will get the speed, but you will not get the direction. Why? Because if suppose the probe is being suspended, whether the fluid is flowing from this side or it is coming from this side somewhere, the heat loss will be the same. So, it will not able to sense that whether this fluid is moving top to the bottom or bottom to the top. So, it will not able to sense that. So, reverse flow condition, if you are using that, you will only get the speed, not the velocity, will not get the direction, and that is the major limitation in the multi-phase flow. Because of the bubbles or discrete phase presence, the flow can reverse at any moment. Okay. So, that is the major drawback, and that is why the more advanced technique is being invented and which will be discussed later. Thank you.